Again, hello to everybody. And you see the first picture is really the entry point for myself into the passive house arena. As Andreas said, I had the opportunity to design the first certified passive house in the Americas in 2005, opened 2006. It's the Waldsee Bio House, and it was built at the Language Village Camp called Concordia Language Villages in Bemidji, Minnesota. That is climate zone 7, and it is part of Concordia College out of Moorhead, Fargo, Minnesota, North Dakota. And it is in the German village. They have numerous villages where they do immersion language learning. The project was funded by numerous foundations, but the main funder was the German Foundation for the Environment, which is a semi-German government organization, one of the largest environmental foundations, definitely in Europe. They typically don't fund any project outside of Germany, so this is one of the very few. But the goal really was to take the immersion learning which Concordia had expertise, and merge it with environmental and climate related issues. And so the collaboration here was that the college would develop a learning program while the foundation would help them to fund the project. And as such, I, over those years at that time and now over the past 15 years, I have quite a bit of relationship to the German-speaking high-performance building manufacturing scene. So I started then with my oldest son an import business a couple of years after, because a lot of people started calling me and asked me where I got my gear. And so here is my story of gear, primarily gear focused on windows and shading, because I think these are the most critical component in any high-performance window. So with that, I'll start here. So to talk about windows, windows are really driven by the available technology to us humans, and glass is the critical one. So for a long time, only very small panes of glass were possible. If you make now the leap in today's, and I look at it from a residential point of view, but the same thing applies to commercial. We typically install what I call box windows. It's a window that you push in from the outside into an opening and finish it on the inside. You compare that with what I consider a box window. That's a European window. It's a frame window, meaning that you have to finish the outside and the inside to it. So you set it somewhere in the middle of the wall in an appropriate location, and I get to that here while I'm explaining it. But basically, you have these two kind of variations of windows in principle. The next thing is, we all know if we do high performance and talk about energy, it's all about heat transfer, so convection, conduction, and radiation. If you build a whole passive house or you're looking at the window, fundamentally, these principles apply. So a window or a window opening or door opening for that matter is basically a small passive house. So you have radiation, conduction, and convection. You have thermal radiation and you have solar radiation, and that's what we're trying to make use of. And if you kind of put this in a wall, this is kind of how to make this transparent. We know all this graph. So this is now a true high performance window. We have the frame, and that's why where the frame window really its advantage is you can actually over insulate the frame. You make the frame part of your wall assembly, so there's an integration happening. You have the frame itself, and that is a component to be talked about, and then of course you have the glass. Now you compare that to not so high performance window, and this is actually in a college dormitory that received LEED Silver rating. You see that you have issues here of potential condensation. You have potential component failures. You even have the risk of mold and health-related issues. So starting to insulate and make super and high-performance windows buildings the issue truly is it's not as trivial as many people make it sound, and the bug is in the detail. So and probably the point to be made, next to the issues in blue, you also have potential comfort issues. So getting it back a little bit into the history of passive house and passive house windows, Feist, when he figured the passive or defined the passive house, he started to define clear components to reach his target of 15 kilowatt hours per square meter heating energy. And of course, the most critical component or one of the most critical component next to the ventilation system is the window. And so he defined in the late 90s the window components, and they're really that 0.8 overall window target he has set for certification of windows really was based on available glass technology at the time and not available frame technology. So this is, I believe, the first certified passive house. We used it at the Bio House. And you see how elaborate the frame construction of that window is. It's still, in my eyes, one of the most beautiful windows ever created. It's just very, very expensive. But the key component is really the line underneath. It says their first passive house window. The 0.7 glass technology was really leading edge at the turn of the century here. And so finding a frame that meets that to get to an overall 0.8 was that. If you compare that now with today's typical passive house window and you go straight to that line below, you see our typical glass is 0.5. So there's truly less pressure on the frame than it was 20 years ago. And so this really means that the technology could be developed more around the glass because the glass outperforms the frame in many or most cases. So that is a cost opportunity, but at the same time, it is also a window development opportunity. And you kind of see how we've taken it from our point of view of Tanner windows. You can see that one could say, okay, is there a way to value engineer this frame away so I basically only have glass exposed to the exterior? And that's, of course, then the third generation of passive house windows, which is our Vitra Premium, which you see installed in the wall basically for a fixed window and an operable window. It basically has no frame exposed to the exterior. So in overall performance aspect, this is probably a superior window. Again, we now, many people probably know, go the direction that it costs more than the typical frame window I showed you before. It just gives you a sense. And if you keep on driving this to the extreme, this is our newest now, the frameless fixed window. You can basically just make glass openings with just the operable as being framed. And that would look like this. Of course, in the metal frame world, you have these frameless windows, which we represent with Fine Line, which you can do now very, very large, almost just glass looking buildings. And really what that means is that the whole frame and the whole frame technology starts to move into the wall and becomes an integrated part of the wall. So the whole detailing is now more involved than just pushing a window in like the typical American boxed window. You can do the same thing in curtain wall. Here we represent the Ryko system. You see how this performs again as the heat transfer here shows. It also shows that you can do very cool stuff. You know, we're one of the few who had the opportunity to build a glass box. Now, the simpler it looks, the more complex it gets. I will stress this at the end again, but fundamentally, it really requires an integrated approach. To make this happen here, you can imagine that this is actually a bridge. So the deflection of the structure of that glass box with minimal shear in the exterior wall or none, glass corners with no support for the cantilevered roof has deflection that is above and beyond any curtain wall or glazing component. And as such, finding a slip structure in this area that the roof can move differently than the supporting glass structure is not a trivial undertaking and takes time, and therefore also accrues cost. So this is not an inexpensive building, even though it looks just very, very simple. We have the opportunity as a company that I work, it's a family operation. You know, my son Robert does sales. I support efforts in the technical, on the technical side, and my second son, Seth, runs a construction company. So we do actually the full vertical integration and have the equipment to do all the large and complex installation. To get back to the technology you're probably interested in, I tried to dig a little deeper here. So fundamentally, windows you can get in these typical frame components. There's man-made fiberglass PVC frames. You have the whole wood-clad system, and you have the metal technology used for frame. We only sell the wood and the metal because the man-made typically has limitations in size before they need to put structural elements in. Then those structural elements become metal, and then they struggle with performance. So this is definitely a very viable option for a small to mid-size punch window. But as soon as you get to more complex configuration, the technology has its limitations. So we kind of stay on the wood and metal side. So if you have any questions, I have less experience on the man-made material than I have with the others. A small point to be made, if you build a passive house versus a standard frame, and you can use these days both, because with the high glass performance, you get still quite good overall window performance. The over insulation, of course, becomes interesting. So we know all about thermal bridging. So if you then look at the cladding, where that is at, of course, a true passive house frame has as minimal cladding in the over insulation part as absolutely necessary. We kind of reduce that in the standard frame, but if you look at the typical frames, they're all fully clad. And if they then, of course, incorporate in the wall, you basically have a thermal bridge, which kind of defeats the purpose of the frame window and its advantage in the first place. So that's just something to consider when you look at different provider of high performance products. If I dig deeper into it, a tilt and turn window here, a cross section of it, you kind of start to see, so the hardware is usually in a particular location. Most Europeans use tilt and turn, so they're all inside toward the inside opening. Of course, because you have over insulation, making them to the exterior opening is counterproductive. The second thing, if you then have a window, you need superior seals. Typically, there are 2 to 3 to even 4 opportunities to add seals to a window frame configuration, and that has to do with how the frame is actually configured in profile. And I think the most critical piece to understand with European windows or these tilt and turn windows is that they all have a water drainage layer. So they are not built to be absolutely watertight. They really have, on the high wind and rain loads, they receive water, and then that water drains out toward the sill. And I get to the installation and sill detail here in a minute. But the critical piece is really the capacity of that. And if you have very strong winds and a lot of rain, the issue then is that you have overload of that, and it can mean that the wind pressure pushes water into the system. So we have added a second drainage layer, one of the few here in the market, to accommodate that, to that minimal event. But it's definitely something to consider depending on your geographic location. Of course, if you're in the desert Southwest, less so than if you're in the northeast of the States with a lot of rain. So now to the installation. Typically, frame windows are installed with bolts. I mean, they are massive frames. So the advantage is that you have less this S-curve kind of issue with the traditional thin structured box windows. They're like 4x4s you install into a structure. So you can use these bolts to really truly level and plumb the window into the wall. It usually has a seal on the inside for air tightness. Many of you know that. It, of course, gets foamed in and insulated in the gap. It usually attaches a water seal to the exterior of the frame, wherever that location is in your building you define. And then it adds a sill to it. And I think that's the most critical piece is understanding that that water drainage area I pointed out before, that allows to be drained off appropriately through a sill, can be any configuration. We typically provide, at least in our proposals, a placeholder for the typical European aluminum seal. But this is kind of like the basic installation component of a window. Now let me transfer the point from frames, and we can talk more about frames. Ask me questions. I know I didn't talk about doors and door opportunities and hardware opportunities, so one can go left or right here in the frames on the frame side. But now I like to kind of briefly touch on the glass. So glass is really what makes it a passive house. Is the critical thing, as I pointed out. Glass technology is where things have happened. It still operates under the principle I pointed out. The glass is really the piece where the solar radiation is added to the three pieces below. And to understand glass, you have to understand how glass is made these days. So typical float glass is made in an operation like this. At the end, you have a sheet that is about 3 meter 20 by 6 meter, or about 10 by 20 feet. And it's either standard glass or white glass, which enters into the building sector. The standard one has a little more iron content. The white glass, it is kind of moved, or it's tried to eliminate some of it. And the float glass here, so the molten glass is really floated on a pool of metal, molten metal, and then cooled off and cut into these sheets. The second piece here in this whole operation is the coating environment. This is a coating machine. This is nanotechnology here in vacuum. So the first major point I like to make is this is all major investment. Whatever we like to have maybe done, you have to find a very, very particular with the newest machine to maybe get something that you don't get anyplace else. Otherwise, the market really defines what you're going to get. It's the first piece. And the second piece, to go slightly into left field, is it takes an awful lot of energy to make this glass. So you have a pretty large amount of embodied energy. And to give you a sense of this, as Andreas pointed out, I have many hats. So one of the hats is I'm associated with a company called Intep. It stands for Integrated Planning. It was started after the first energy crisis in the late 70s. So we just celebrated our 40th anniversary. And primarily focused on consulting, and the consulting expertise we have, which is quite unique in the world, is our forte is deep understanding of the material flow through the life cycle of buildings. So energy for us is energy flow, but we have material flow, we have labor impact, and so on. And so understanding embodied energy, we have scientists that in our company do applied science. And so they're involved in this whole thing. And we had the opportunity in 2012 work for the city of Vancouver to help them to transfer their targets and goals from their climate action plan to actual application in the built environment. So we worked with the University of British Columbia, the province, to work on setting energy target for operational energy and for embodied energy. And so that's why they are where they're at. I believe our work, who was funded or partially funded by the development community of Vancouver, the work was therefore all around high-rise and mid-rise residential. So the data I'm going to show you here, and just to point out here, it's primary energy, so it's not useful energy. That's why the 50 kilowatt per square meter don't add up to the 15 passive house target, because there are two measurements on the energy flow chart. But nonetheless, I don't want to get into the number detail. I want to just demonstrate the magnitude and the issue of embodied energy. So first, if you don't tackle, and you see in the red bars, you don't tackle the operational energy, you don't have to care about embodied energy. It makes no difference. You can save that in a multifold by factor in the operational energy. But if you get into the passive house arena of operational energy reduction, and that is the 2050 projection here for the city of Vancouver at the time, you start to see that tentatively the embodied energy increases because you just add additional components like insulation and glass or glass technology to it. So it has a true impact on it. Now, how embodied energy really works to be managed is not as simple and as trivial as a passive house or an energy calculation, because it relies on data from the industry, how it is really produced, transported, and installed. And so since every technology has different ways and means for manufacturing energy to be provided, and what the source of that is, you have different data from the manufacturing part that basically North America is mostly not available. In the European environment, there's an ISO norm, and you can get an environmental product declaration from many to most company, not all, because of the same reason North American company wouldn't do that. And without this data and the database, you basically, all the embodied energy calculation instruments are pretty much worthless. So, and since we don't get the data, we don't have a data bank. So even if a company like Athena and they're based in British Columbia, and it's probably the best available North American embodied energy tool, their data is very, very limited. So their information is not very useful. Long story short, so sorry for dividing off, we can have this conversation too, and I probably could have a workshop on that, but I thought it's just important because we're talking about glass, and glass is a big embodied energy piece. Going now to the two critical values we look in the glass, and it does for us, of course, it needs to do the same thing as the frame and the wall of a building. It needs to tackle convection, conduction, and thermal radiation. But here, at the same time, now we're playing with the solar radiation. So to do the blue ones in the thing first, that's the U and the R value. So the convection, conduction, and thermal radiation, these are basically coatings. You get them on the inner side of the inner pane and the inner side of the outer pane. They're here commonly known as low E coatings. They're typically silver-based, and that's what drives the price. The second piece, as probably all of you know, is the filling. The components for high performance are the noble gases, argon, krypton, and xenon. And as the order goes, argon the least expensive, krypton about 10 times, xenon about 100 to 500 times more expensive, or in that magnitude. So trying to go to the heavier gases, good thing, it's just cost driver. You also see the heavier, the thinner the air gap can be. So this is why you also see that, of course, that North American supplier then go quickly to the thinner pane, double pane with the higher, with the heavier gases to try kind of compete in the UR value competition. But at the end of the day, the least expensive way to get really high performance glasses with argon. And Feist already defined that also in his original, targets and requirements. You typically can get from a supplier a glass spec sheet. You find typically the coatings here listed someplace. They're listed here. Each manufacturer has their own name for it. So it's a name game. And then you see up here the gas filling, argon, or all these gases are typically 90% or a mixture of. You can get argon krypton, you can krypton, and so on. There are tools out there. You can play with this. Some of these glass manufacturers can give you access to, but it results in a new value, sorry, and the solar heat gain and light transmitting values I'm going to get to next. Before I get there, of course, many of you might heard of vacuum glass. It's most common these days in China primarily. It has a certain cost, technology interest. It's been on the market for over 20 years. I've seen the first vacuum glass in the late 90s, early 2000s. They're basically two panes of glass with these little dots. There are spaces in between. You see the space in between is, part of a millimeter. And then the vacuum is really the place where the insulation value comes from. The issue with these is the size is in most, by most manufacturers limited to the size how they can manufacture. Meter 50, so 5 feet by 8 feet is about where they cap out. I don't know of many who'd make them bigger. And the biggest issue is, of course, the edge, because that's where you seal the vacuum in. And so there's some issues in this particular technology, and we can talk about that. Which leads me to the edge condition. So the spacer is, I think, one of the most critical undervalued components. They're very, very hard to get here in the US. I don't know many or any really insulated glass unit manufacturer that stocks super insulating spacers like a Swiss Spacer Ultimate. They're standard in any European manufacturing plant. So for us, we struggle with that tremendously. So we produce everything in the US, in Europe, due to some of these component limitations here, and that's really driven not by technological limitation. It's basically a market demand limitation. There are many things one can go down. Glass can do many things. On the coating side, I can coat for UV. I can coat anti-glare. So you can make glass that you don't see if it's very clean, and people can run into it. That's probably the downside. That's what birds also do. So anti-bird strike is a coating. You can go to smart glass. So you can put current to it that you can change the tint or the solar heat gain coefficient on it, and so on. So fundamentally, there are other coatings. You can treat glass. Heat treatment is probably the most well-known for security reason. And on the security side, you get to the lamination for the same reason, security. But you can do it for sound, bullet, hurricane. You go down the list. There is a whole list here, and that can be endless in itself. So I move now to the second piece here is, and I think that's what makes the passive house a passive house, is really making use of the free solar radiation. And so if you are in a climate that is cooling load driven, the typical and traditional response to that is that you coat for that, and you do that on the inner side of the outer pane. And you can reduce that into 30%, 25, 20% solar heat gain coefficient. The more that goes, or the lower that goes, the more expensive typically these coatings are. A personal note to this here, and I added the light transmission value to it. Of course, the lower the solar heat gain, the more it becomes like sunglasses. The more the tint you have in the glass and the sunglasses, the less light comes in. And that's the light transmission value. So the light transmission value also gives you a sense of clarity of glass. And if you look to the capacity of coating equipment or their age, this is really the interesting place to look at it. See how low the solar heat gain coefficient is in respect to how high the light transmission value is. That means the clearer one can make sunglasses, the better and newer the equipment is, because that's really where the newest coating technologies have made advances in the last decade. So as I pointed out, these are these pieces. You find it again here, under the coating side. You see here, it's again a Saint-Gobain Cool Light Extreme is the most typical one we use. It has still a light transmittance of almost 64% to a typical of 70, but you have a solar heat gain or a factor of down here of 0.31. So that's probably as good a spread I know and I have seen. These coatings might be different in the European environment than in the North American environment. I know I would struggle to get some of this out of a North American factory setting. And that brings me to the second part of my presentation, why I combined these two components here, is there is a way to have the cake and eat it too. It's called exterior shading. We typically use Venetian blinds, and I'll just explain to you why. As I said in my other things, we can evaluate and calculate the solar heat gain coefficient of any fixed shading all the way to trees. We don't use them because of the control over it much. We just use them in calculation to see what we might lose in solar heat gain on the heating side. But other than that, trees are great things and they do work. I'm not arguing that. It's just a little too uncontrollable for my personal taste, but that is a personal preference. So exterior Venetian blinds is for us the starting point for exterior shading, and this is the reason why. So from the 100% solar heat gain, I can basically turn this off. And if you look at it, and I'm just showing you here a building here going through, the point I want to make is the control you have. So I can basically either shut them off at night to have it dark, or I can shut them off during the day to shut off the solar heat gain if I don't need it or don't want it. I can control light transmission still for working and the sight through the window. Yes, I still have some obstruction due to the blinds. But at the same time, I have stringing capacity that I can even use the blinds for light shelving to get light in and still control solar heat gain you see in the work graph down below. And if I go to installation, basically they're installed to the exterior. In passive houses, because we have a very deep cavity, it's easily to incorporate them that you're in a pocket situation that you don't see them in a retrofit. So that's the graph all the way to the left. If you see the graph here second to the right, you see the most typical retrofit solution. You can also add them at any time to the building after the fact. The critical issue is really just the motorization, the power to it. Here's a typical detail we do, and you see how that fits into a TGI here, 10-inch. So there's plenty of space for them. It's typically about 5 to 6 inches of width you need. and we still have ability to over insulate the frame. Should you don't have that, we also sell vacuum insulation panel. That's R28. You look up that information on our website. Just if you don't have the space for insulation, but you need super insulation, that's a great material to use. It costs about the same factor. It offers more insulation per inch in cost to that insulation. So it's not inexpensive. So it's probably not used for insulating where traditional insulation can do the job. But if space is of value to you, so either by real estate value or by aesthetic, technical, or other issues, this is a tool that is, or a material and tool that it was not available. I mean, it's been available in Europe for 20 years, but I believe we're the only supplier at the moment for the North American market of this product. Alternatives to the Venetian blinds are fabric blinds. You lose some control over light and see-through. You have to pick your fabric for that reason. So the density of the fabric gives you also the reduction in solar heat gain. So you can play with that a little. Here, a typical installation, how that would see. The nice thing, because it's rolled, it takes up much less space. And then the last piece to get to the shading pieces that always comes up and most people don't understand 100%. It's pretty simple. I like to keep it on that level. Here, each one is a rabbit hole. We can go deep. But all our shades are motorized. There's no crank because the crank makes a hole in the building. We can have holes in the building. In passive houses, you guys know all that. So the motor is pretty simple. It has no intelligence. It basically has two power feeds. That means the power comes in one way, it turns right. The power turns the other way, and it goes left, meaning it either goes up or it goes down. That's it. So the next piece on this one is something has to control that. So that can be a switch you can do up or down, or this can be a motor controller, which you see here. And this is a wireless motor controller. Your control company will provide you with, from here on out, with everything if you want to do that. So any home automation system should be able to handle it. If I go to Lutron, point out they struggle with the climate control, but other than that, Homeworks does that just fine. They have all the components for it and you can incorporate it. So a motor controller. The next thing is what I just mentioned, shades. The only risk shades have, and that's the major risk. It's not snow, it's not ice, it's not rain. Those are all good ideas. No, the only a major issue these have is wind. So you do have to add, and that's why we highly recommend that any automation is automated with a override wind sensor. This is now a climate sensor, so it also registers solar, and then you can program all sorts of stuff. Don't want to get to the programming piece. We can tackle that in Q&A. But the main point I'm making is you have to install and commission the system so that the maximum wind the system can sustain. That depends on the wind rating of where you build, the exposure and direction to that wind, the location of the shade, how high above ground, what's surrounding to it. This is kind of setting that wind speed. Typically, they kind of cap out. The ones we sell is the most wind stable ones available. They cap out somewhere around 25, 30 miles an hour or somewhere thereabouts. So a little wind doesn't hurt, but as soon as you have a winter storm approaching, or mostly a summer storm approaching here, you want to make sure that when you're not there, somebody moves these shades up, otherwise they break. And the last thing, is, of course, on the whole control thing is the user interface. This is a wireless system we sell on the Lero side, but as I said, there are many hardwired and other wireless solutions on the market. And however they interface with the motor is the way to go. So you can do that on your own. that gets me to the almost to the end of it. I show you here your passive house verification sheet here, the window page, to just kind of point out the key summary of it, why a passive house or a high performance building is what it is. And that is that transmission losses on the windows are substantially less than the heat gains. And this is basically the free heat. There's nothing cheaper than free. So here it is. And my only point to this one is high performance building require an integrated approach. So you can buy good individual components, but if they don't are incorporated in the building in such a way that it's a win-win for the whole system. So it's a system optimized solution, not a component added solution. You have less chance of the performance you're looking for than the other way, and with high likelihood it also costs more. So the question of cost of the component is not necessarily always just the cost of the individual component, but how it's really integrated into your building. And with that, that's kind of my thing here. Any questions? Please feel to ask. Let's start. And if you have any questions or want to contact me afterwards, here are my contact information.
So thanks, Stephan, for the fantastic presentation. So please, everyone, you can unmute yourself if you want to ask a question yourself, or please post the question into the chat box and we'll take it from there. I have one question. You showed that beautiful building, the glass box on that stone base building. Oh. Was that a passive house or passive house, close to a passive house kind of a building, or?
No, I don't believe we ever talked about passive house as a guiding principle, but the architect and the owner were very interested in comfort and environmental impact in their own way. And as such, it was very important to them to understand what that means. And they quickly came to the understanding it really required triple pane high performance windows. And then I can't recall, because it's been now a couple of years, how it reflected really in the wall assemblies below. Roofs are typically well insulated, so I can't speak to it beyond that.
Mm-hmm. And so you show us a couple of buildings with the exterior shading, which is not really like a common thing here in the US.
Yeah.
Do you sell it to a lot of clients? What's your experience with using them?
At the moment, I think we're one of the last reputable, representative of a large reputable European company and of exterior shading devices. That market has kind of concentrated itself to two companies that really tackle the geographic area where that culturally is common. So I think that the whole exterior shading is a building cultural issue as much as it is, and therefore then also a builder user cultural issue. So if I speak to, for example, the German speaking European is a very center of this for sure. I mean, there are others too. I mean, the Dutch or the French and so on. I don't want to get here too cultural, but there wouldn't be a homeowner where that's not a base, that's in their base budget. Here in North America, companies come and go, and they come and go because, as you just mentioned, Andreas, nobody considers it. Well, considering is probably the wrong word. I think exterior shading is considered. It's considered conceptually. It's less technically understood and calculated as the PHPP calculates it for you. Therefore, the product as we sell it now, even to passive house projects, I'd say I don't know. We don't sell much. I mean, we have it in our product offering because we think it's very important, but it's scary how little it's used. And I'm thinking now the more it gets used, probably start to get calls from the end user or the homeowners who start to point out that they overheat their house. Because our experience with that goes also to solar heat gain coefficient. And I didn't mention that, but in the beginning time, so about 10 years ago, so the second, third, fourth, fifth projects we did here in the upper Midwest, because we're in climate zone 6 and 7, we of course would like the solar heat gain coefficient of not the typical 50%, but you can go 60, 65 and more percent. That sounds incredible because it really, you see it in the PHPP, you go, yeah, home run. Now I really got the heat gain. But what we noticed building a couple of these with that glass is, and it's the one of them is the one I showed you where you see the exterior shading here opening and closing and going down. That has that. I mean, at 20, 30 below outside, blue sunshine, we have in the afternoon, we can heat this building up to 80 degrees. It's just scary how quick you make a sauna out of it. And that's at very, very cold temperatures. So if that client wouldn't have exterior shading devices to manage that heat gain, that is really, really tricky. So we kind of went off the solar heat gain, stay with the 50%, because for us in our climate zone, that's pretty good sweet spot. We can get all the free heat we need in the wintertime. And then we only install or do passive houses with exterior shading devices. But ending that answer piece here and the long-windedness of it is of course, it costs, let me say, on a single family home, somewhere between, on the low end, probably $10,000, on the high end, probably $20,000. With very simple controls. You get more expensive in controls, you add a few thousand quickly to it. So it's a budget item that is just in no normal budget, and the window's already expensive, so why would one add another expensive component to it? And that's the typical reaction, and that's all I can say. I wouldn't do it this way, but it's done every place that way.
Yeah. So I think the window, obviously, and the solar heat gain coefficient is an important consideration for any building, but especially for passive house buildings. We do see actually overheating in the wintertime as well. But of course, with the heating climate, overheating or heat protection in the summertime obviously will become a much more important issue. Therefore, exterior shading might become a more interesting subject for buildings in general. I don't see any other questions. I would like to thank Stephan for your very informative presentation, and we'll send out the recording to everyone, and Stephan will also follow up with you guys and send you a certificate of participation, and you can always ask him more detailed questions about the product directly with him. So with that said, thank you everyone for listening, and thanks Stephan for the presentation.
Hey, thank you everybody for participating. Have a great day.
Thanks. Enjoy.
Stay healthy.
Absolutely.